Welcome to the 2017 Science Olympiad National Tournament, and welcome to the campus of Wright State University. Let us welcome each of our teams with the Parade of States. To help us out with that, I'd like to introduce Dr. Douglas Lehman. Dr. Lehman is the Dean of Wright State's College of Science and Mathematics. He's also an immunologist, specializing in researching the biochemical and physiological aspects of host-virus interactions.
Thank you. It's an honor to be here tonight celebrating your achievements and the passions we all share for science. In the Parade of States, representatives from each of our 121 teams will be announced and welcomed into the arena. Please show your support with your applause. First up, from the state of Alabama, Auburn Junior High School. Auburn High School. From the state of Alaska, Colony Middle School. Matsu Career and Technical High School. From the state of Arizona, Paragon Science Academy. University High School. From the state of Arkansas, Lisa Academy Charter School West. Little Rock Central High School. From the state of California, Oak Valley Middle School. Troy High School. Winston Churchill Middle School. Mira Loma High School. From the state of Colorado, Preston Middle School. Fossil Ridge High School. From the state of Connecticut, Old Lyme Middle School. Hopkins School. From the state of Delaware, H.B. DuPont Middle School. Charter School of Wilmington. From the state of Florida, Archimedean Middle Conservatory. Boca Raton Community High School. Orlando Science Middle School. Archimedean Upper Conservatory. From the state of Georgia, Dodgen Middle School. Brookwood High School. Sports Academy. Chattahoochee High School. From the state of Hawaii, Highlands Intermediate School. Iolani School. From the state of Idaho, Treasure Valley Home School. And Treasure Valley Home School. From the state of Illinois, Daniel Wright Junior High. New Trier High School. Marie Murphy Middle School. Adelaide E. Stevenson High School. State of Indiana, Thomas Jefferson Middle School. And Munster High School. From the state of Iowa, Ames Middle School. And Mount Vernon High School. State of Kansas, California Trail Middle School. And Olathe North High School. From the state of Kentucky, Russell Independent Middle School. High School. From the state of Louisiana, St. John Birchman's Catholic School. And St. Martin's Episcopal School. From the state of Maine, Metamuk Middle School. And Waterville Senior High School. From the state of Maryland, North Bethesda Middle School. And Centennial High School. From the state of Massachusetts, A.W. Coolidge Middle School. And Acton-Boxborough Regional High School. From the state of Michigan, Meads Mill Middle School. Northville High School. Baker Middle School. And International Academy Central. From the state of Minnesota, Chippewa Middle School. Mounds View High School. From the state of Mississippi, Germantown Middle School. And Cathedral High School. From the state of Missouri, Ladue Middle School. Ladue Horton Watkins High School. Wydown Middle School. And Pembroke Hill Upper School. From the state of Montana, Clancy School. And Helena High School. From the state of Nebraska, Mission Middle School. And Lincoln Southwest High School. From the state of Nevada, Hyde Park Middle School, Academy of Science and Mathematics. And Ed W. Clark High School. From the state of New Hampshire, Walpole Elementary School. And Merrimack High School. From the state of New Jersey, Community Middle School. West Windsor, Plainsboro High School South. From the state of New Mexico, Albuquerque Area Homeschoolers. And Albuquerque Academy. From the state of New York, Eagle Hill. Fayetteville, Manlius High School. Paul J. Jelinas Junior High School. Columbia High School. From the state of North Carolina, Piedmont 1B Middle School. North Carolina School of Science and Math. J. Carnage Magnet Middle School. And William G. Enlow High School. From the state of North Dakota, Watchter Middle School. School. From the state of Oklahoma, Cassidy School. And again, Cassidy School. From the state of Oregon, Stoller Middle School. And Westview High School. From the state of Pennsylvania, Springhouse Middle School. Harriton High School. Shady Side Academy. And Baird Rustin High School. From the state of Rhode Island, Gallagher Middle School. And Barrington High School. From the state of South Carolina, Clinton Middle School. And Clinton High School. From the state of South Dakota, Yankton Middle School. And Yankton High School. From the state of Tennessee, Bearden Middle School. And White Station High School. From the state of Texas, Beckendorf Junior High School. Liberal Arts and Sciences Academy. Keeling Middle School. And William P. Clements High School. From the state of Utah, Fairfield Junior High School. And Maple Mountain High School. From the state of Virginia, Longfellow Middle School. And Fairfax High School. From the state of Washington, North Shore Junior High School. And Camas High School. From the state of West Virginia, Huntington Middle School. And Huntington High School. From the state of Wisconsin, Hamilton Middle School. Medford Area Senior High School. Wyoming. Riverton Middle School. And Kelly Walsh High School. From your host state of Ohio, Tower Heights Middle School. Mentor High School. Solon Middle School. And Solon High School. From the country of Japan, Gifu Prefectural Gifu Senior High School. Let's hear it one more time for all of our competing teams.
Please rise as we honor America with the singing of our national anthem. I'd now like to introduce the new chair of the Wright State University Board of Trustees, Mr. Doug Fecker.
Thank you and good evening. How are y'all doing tonight? It is indeed my honor to welcome all of you to Wright State University. I hope you love it here because we who work here do. You've all worked incredibly hard to be here. Your dedication has paid off and you've made it to the Science Olympiad National Tournament. You should be so very proud of yourselves. You know, we have a day of exciting competition ahead of us tomorrow, and many of you have already competed in some trial events today. What excites me most is that we have more than 2,000 competitors here this weekend, representing all 50 states, and I just love our global ambassador team all the way here from Japan. Let's hear it for Japan! a chance to explore our campus a little bit and that you're having a great time here today and tomorrow. We are especially excited to host this tournament because as Science Olympiad competitors, you represent the same ingenuity that helped the Wright brothers, for whom our great university is named, invent the first powered airplane. You know, Orville and Wilbur did not start out as pilots. Heck, there were no pilots before Orville and Wilbur, were there? They were bicycle shop owners. But they were curious, and they were courageous. They were willing to work hard, and they weren't afraid of failure, and you know what? They had no idea what the word impossible meant. They were raised to ask questions. They were encouraged to dream. They became self-trained engineers, mathematicians, physicists, and philosophers. Their passion and undeterred efforts led them to perfect their flying machine in a field just down the road from where we sit right now. And you know what, students? You remind us here of the Wright brothers. I think that's phenomenal. You are hardworking, you're creative, you are problem solvers. You are dedicated to learning and understanding the world around you. You set goals and then spend countless hours working to achieve them. These skills have helped you rise to the highest level of this competition. And you know what? I am quite confident you will go very far in your futures. In fact, Wright State University would love to see each and every one of you here to return as Raiders when you graduate. And to that end, we'll be awarding a $1,000 scholarship to the first place winners of each individual event and a $2,500 scholarship to all official members of the first place teams in both divisions. These scholarships are renewable for 4 years and can be stacked with other academic merit scholarships you might earn. Of course, certain admission criteria and renewal eligibility terms apply, but you can read all about that in your tournament programs. And so we certainly look forward to welcoming you back to campus when you're ready to start your college career. The fact of the matter is we have world-class researchers and faculty, lecturers, the kinds of people that love to watch students learn. I really hope you consider Wright State University. Right now, we're going to show a brief video about Wright State, but first let me tell you the most important thing about who we are. At Wright State University, we believe that every student comes from a unique background and has a unique set of dreams. That's why we've made it our mission to support each individual student on their journey to success. We are nationally recognized for serving students with disabilities, as well as veterans and military-connected students. Our diverse campus community includes high-achieving honors students, international students, older adult students, and students who are the first in their families, the very first in their families, to go to college. It is indeed our #1 priority to make sure that every single one of our students succeeds so that they can live the lives they would like to live. In that same spirit, we also want to help you succeed this weekend. Our faculty, staff, and students, as well as many from the communities we serve, have come out this weekend to volunteer their time so you can have a great experience on our campus. So on behalf of the Raider family, we wish you the best of luck in your competition tomorrow, and in all of your endeavors in the future. We certainly hope every one of your dreams comes true. Thank you very much.
In the early 20th century, aviation pioneers Orville and Wilbur Wright changed the world. The brothers invented the world's first successful airplane from their Dayton, Ohio bicycle shop. More than a century later, Wright State University carries on their legacy by building a culture of innovation and discovery, with students who are pioneers of potential. We accept the challenge to continue the Wright brothers' daring spirit by believing we can achieve anything. We take risks, challenge the status quo, and continually explore ways to do things better. At Wright State University, we dare you to dream, to inspire, to innovate, and to soar. Wright State University is a public research university near Dayton, Ohio, with a lake campus on the shores of Grand Lake St. Mary's in Salina, Ohio. Wright State serves nearly 18,000 students and offers more than 230 undergraduate, graduate, doctoral, and professional degrees. If you love science, you will love Wright State. State-of-the-art facilities allow faculty and students to pursue excellence and discovery across many disciplines. Wright State University is a leader in Ohio for research in neuroscience, human performance, and aerospace medicine. Our researchers work in partnership with businesses, community organizations, and Wright-Patterson Air Force Base, which is right next door. The power of these partnerships is seen in our neuroscience engineering collaboration building, where scientists and engineers work side by side to take research from the bench to the community. It's home to the Wright State and Premier Health Partners Neuroscience Institute, which researches nerve injuries, among other important work. Utilizing computer-based research, the Center of Excellence in Product Reliability and Optimization engineers new products for success. The Knowledge-Enabled Computing Center, known as NOESIS, is a leader in research that associates meaning with big data on the web, enabling people to find, share, and connect information easily. University research also generates technology that affects human impact, like a virtual game that helps train for cultural competencies.
You can hear my voice and walk.
Wright State is helping to save lives by training military and civilian first responders at our National Center for Medical Readiness at Calamityville. The College of Nursing and Health collaborated with the U.S. Air Force to develop the nation's first master's program in flight and disaster nursing.
Put this on here to block the hole, okay?
Nationally recognized for its commitment to community service, the Boonshoff School of Medicine offers innovative medical education. And the School of Professional Psychology is known nationally for its innovative programs. Wright State has so much more to offer. It is an innovator in the arts through Celia and its Distinguished Visiting Artist Series. Graduates have gone on to win Emmys, star on Broadway, and create award-winning movies.
I hope that this building spurs the students that come here to working harder than they ever have in their lives.
Our film center is even named after Academy Award-winning actor and director Tom Hanks, who came to campus to work with film students. Academic service learning courses, study abroad opportunities in over 40 countries, internships, and co-ops allow students to learn while making a difference in the real world. Wright State has been recognized nationally for its business education and community service programs. The university is nationally recognized for the unprecedented support it gives to students with disabilities and to veteran and military-connected students. Hardworking, ambitious students take advantage of the Honors Program, which provides small classes, a supportive learning environment, and opportunities for service learning and studying abroad. Wright State takes pride in its beautiful 557-acre campus, which includes a biology preserve. And we're also committed to environmental stewardship. And our students have fun. Cultural groups, art galleries, and the Wright State Nutter Center, which has hosted the likes of John Legend, Fall Out Boy, Kesha, Jason Derulo, and Brad Paisley, will keep your calendar full. In a single day, you can rock climb, take an indoor cycling class, swim in the Olympic-sized pool, paint murals, and cheer for the Raiders. As Wright State celebrates its 50th anniversary, we are confident the best is yet to come. You too can become a pioneer of potential at Wright State University.
Please Please welcome to the stage Dr. Gerard Putz, President and co-founder of Science Olympiad.
Good evening and welcome to the 33rd Annual Science Olympiad National Tournament, hosted by Wright State University, one of our nation's premier science and technology universities. This is the second time Wright State has hosted a national tournament, and we're thrilled to be back. When we were here 4 years ago, we could not have imagined that the seniors who participated in the 2013 tournament are now graduating from college, on the road to realizing their dreams of becoming a scientist, researcher, engineer, doctor, or teacher. We're very proud that Science Olympiad was a part of their pursuit to realize a dream, and we hope to be part of yours. Whatever path you choose, this weekend is much more than a competition. It is a stepping stone to mastering the qualities that brought you to Wright State tonight. Your thirst for knowledge, your curiosity, and your imagination. Those skills will provide you with the way forward on the road to become leaders, visionaries, and innovators. In the next decade, with the students in this audience provide a new algorithm, the hottest piece of technology, the medical breakthrough that cures a disease, or the invention that takes us further into space than we've ever been. Only time will tell, and we can't wait to cheer your success. Speaking of success, I'd like to extend a special welcome to the students and teachers from Gifu High School who won their version of the Science Olympiad, called the Japan High School Science Championship, in March. For the 6th year in a row, this global ambassador team from Japan has traveled across the world to be part of Science Olympiad's national tournament. And tomorrow, they'll be competing as guests in 4 events. Before I go, I want to take the time to acknowledge, congratulate, and thank all of the adults in this room. The Science Olympiad officials, directors, supervisors, sponsors, parents, and coaches who helped get you here. We thank them for their tremendous dedication, support, and leadership to make Science Olympiad the best it can be. And I can't forget the Wright State University Tournament Planning Committee either. They have been working daily for months to make sure this weekend will be one you will remember for the rest of your lives. Let's give the big round of applause to these folks. In closing, I have a special token of our appreciation that I'd like to present to the Wright State, and to accept this award, I'd like to reintroduce the Vice Chair of the Board of Trustees, Doug Fecker, who represents the entire academic community of this great institution. The plaque reads, Science Olympiad, presented to Wright State University for your support in the recognition of excellence in science education and student achievement. Science Olympiad National Finals 2017. Thanks, Doug.
Thank you so much.
Thank you. Stand for a picture. Oh, yeah. We're not very good at this.
Thank you. Thank you so much.
Thanks.
And now, I'd like to introduce Dr. Elliott Brown to give our keynote address. Dr. Brown is a Wright State University professor in physics and electrical engineering. He's also the endowed chair of experimental sensor physics. He has received numerous grants and awards for his research on terahertz science and technology.
Very much. I'm extremely honored to be here tonight and represent the scientific community. I just wanted to start by thanking my immediate mentors, Dr. Lehman, my dean in the College of Science and Mathematics, Vice President Fife, and my department chair in physics, Dr. Deibel. I'm so happy to hear about the history of the Wright brothers. It's what brought me here, in part from California. I came from the University of California, the #1 ranked institution in the United States. Why did I come to Ohio? Not because of the Wright brothers, maybe a little, but because of a very special incident in my life, 1969, July. Many of you are either getting born or near to be born. It was the landing of the first man on the moon. His name was Neil Armstrong. And one of the reasons I remember that so specially is because it was the excuse for my father to buy a color television. 1969, I got my first view on color television, and our first view was the Apollo landing on the moon. But my message today is a little more generic than that, because one thing that has guided me from that day on is science does not disappoint. At that point in time, I said, I'm going to be a scientist, and I have never had it disappoint me in my whole life since 1969. And part of my message today is science is complex. And more recently, science has become interdisciplinary. And my talk today is about that interdisciplinary nature that is becoming very popular. In fact, the interdisciplinary nature is even picking up momentum at the highest levels of investment, like Silicon Valley, where I came from. Silicon Valley, which decides so many huge investments in new startup companies and follow-on companies, is now investing in a new field called biomedicine and biotechnology. So my talk is about that, because I'm trying to inspire the future, not just talk about the past. So with that in mind, let's talk about biophysics. So traditionally, there has been physics and chemistry and biology and mathematics. And now we're in an era where all of these fields are merging across boundaries. And what's so exciting about that is that you can get into these fields without being a world expert. The old model is, if you're going to get into a physics, you better be really good at physics or math or whatever. But now there's these fields where, in between, you can have creative ideas that aren't necessarily world-shattering events. They're not necessarily Nobel Prizes, but they create progress because these fields are new and they're very introductory, shall we say. So let's start off by looking at the interaction of electromagnetic radiation, which many of you know about already, I'm sure. It's of course, very commonplace, with biological matter. And if we look at the electromagnetic spectrum, we have the radio frequency band, we have the infrared band, the visible band, and the ultraviolet to X-ray band. In this lowest frequency band, the radio band, most of the interaction of radiation with biology is by rotational excitation. The frequency and the corresponding photonic energy is low enough that all you do is induce some vibrations or wags, not a huge change. When you get into the infrared, you start to get vibrational excitation, which is very important. When you get into the visible, you start to get electronic excitation. You actually start changing the location, the orbital nature of the electrons inside of atoms. And finally, in the X-ray and the gamma region, where we get all of our X-ray taken by medical doctors around the world, we actually start liberating electrons from atoms, which sounds kind of trivial on first thought, but turns out to be very damaging to tissue. So it's a region in which we try to avoid if we're going to introduce a new technology. So what I'm talking about today is this kind of intermediate region between the infrared and the radio frequency, where cell phones work, where computers work, where we can have a little aspect of each, a little bit of the rotational aspect mixed with a little bit of the infrared aspect. And what's good about this from the perspective of sensing is that the wavelength is in this kind of region 1 to 10 millimeters, which is generally regarded as small enough to create good resolution in medical sensing, but short enough in frequency to be non-ionizing, and so not dangerous to human tissue. So the phenomenology I'll talk about in the next few minutes is, in this region, biomolecules, and I'll define those a little better in a minute, undergo structural vibrational resonances on a picosecond time scale, picosecond 10 to the minus 12, that are characteristic of frequencies in the gigahertz to terahertz region. The resonant vibrations are made possible by the fact that the bonding that goes on biomolecules is very soft, and I use that expression in colloquial sense, in meaning that the molecules are only weakly bonded together. Hydrogen bonding is very typical in biological, in all the cells in your body, oftentimes bonded strictly by hydrogen bonding, not covalent bonding. Covalent bonding is much stronger. The other aspect is that in addition to having soft bonding, biomolecules have very large mass. So when you plug into this very common expression that many of you may have seen in your high school physics class, the resonant frequency of a harmonic oscillator is the square root of the spring constant divided by the mass. It was derived right after Isaac Newton in the 18th century. It is still one of the most useful expressions in all of physics and now in biophysics. So square root of spring constant over mass. When we talk about atomic bonding, like we have in the infrared or visible region, that spring constant is typically 10 newtons per meter. Newton is a unit of force in physics, goes back to Isaac Newton himself. Mass is typically 100 Daltons, order of magnitude, so that typically if you take this square root, you end up with a frequency in the mid-infrared region. That's been known for over a century. Now, we're looking at biomolecules with spring constants of less than 1 Newton per meter, masses of greater than 10,000 Daltons, which leads to resonant frequencies in the terahertz region. And this is all very recent. So one of the challenges in science, especially interdisciplinary science, is that in order to prove new ideas and prove conjectures, you have to develop new instrumentation. So one of the things we've done in the last 10 years or so is develop some unique instrumentation for measuring biomolecular and bioparticle signatures in the terahertz region. And this is a spectrometer technology. We started out in 2007. Now we have working instruments that have thousands of hours of use. And what are we utilizing? We're utilizing other technologies. So another message I want to convey to you, young scientists, is when you develop new science in your field, don't ignore science in other fields. Especially don't ignore technology in other fields, because oftentimes that technology makes a difference in your new field. And this is the interdisciplinary nature of the new world of science that we live in. So we used laser technology that was developed for optical communications and ultimately for fiber optic communications in the late 1990s. And we integrated that into a system that could create terahertz radiation by photomixing, a concept that was developed in the early 1990s. And I was fortunate to be on the first patent at Massachusetts Institute of Technology. And here it is. And here's the performance. And you can see the dynamic range that's made possible in these measurements of 80 decibels at the low frequency end of our range to 40 decibels at the upper frequency range. And if you're not familiar, this would be converted into linear units 10 to the 8th in scientific units and 10 to the 4th. So big numbers. So biological material is very complex. If you study material science and you study semiconductors or metallurgy or any of these fields, you think about unit cells on the order of 1,000 Daltons, maybe. In biology, often these molecules and unit cells are on the order of 10,000 to 1 million Daltons. And so you have to be very careful in biology of how you handle your samples. When you're dealing with metallurgy and semiconductors, your samples live forever. They may oxidize, but you still have that material down inside the core. In biology, it's actually very possible and very common for your materials to die a sudden death. So you have to be very careful for how you prepare these samples. And the two I'm going to show you in the next few minutes are things that are centuries old. Filter paper, which you use in high school biology lab, I'm sure many of you have, and then high-tech. More recently, high-tech, we have figured out how to put biological materials into what I'll call nanofluidic chips, and I'll show you that in a minute. The key point is you want to preserve the natural biology and physiology of your samples while you're doing the experiments, because especially when you're dealing with proteins and nucleic acids, they will decay over the period of minutes. So you have to make sure that your experiment is done preserving those capabilities. So here's our setup. Here's the spectrometer I showed you in just the last chart. And what we do is we put the samples right in the output port, just in front of the receiver of the coherent photomixing spectrometer. What that allows us to do is put samples in and make measurements in a matter of minutes before significant biological decay occurs. So, what is motivating a field? One of the really important questions in science is, how do you survive? So that's another message I want to pass on. Great science does not necessarily survive. You have to be, unfortunately, relevant. You have to impact technology. You have to impact something. And the nice thing about biophysics that I want to push is that biophysics impacts human life. It impacts medicine, which is really cool because nobody, or very few people I should say, question the impact on biology and human medicine. Everybody knows how important that is. It's not cell phones, it's life. And so we got into this field because of biosecurity. I know that sounds a little odd because you may not have heard about biosecurity, you may not have heard about biowarfare. I hate to say it, but it's a reality. But there's a thing called anthrax. It's in the genus Bacillus, and it's something that's been around for millennia on planet Earth. It's been used as poisons back in the eras before Christ, BCs, okay? And it's a simple little bacteria. It's a rod-shaped bacteria, but inside that rod-shaped bacteria are these endospores that I'm showing as little teeny eggs, little white eggs here. And it turns out that the cell is not particularly toxic, but that little endospore is. And the endospore is how this biomolecule propagates. It's how it survives. So when conditions get harsh, the cell dies, and these little teeny endospores are projected into the local environment, and they are some of the toughest, hardiest, biological objects on planet Earth. People have found these in the deserts of the Middle East and have carbon dated them to lives exceeding 2,000 years. The second important fact is these little endospores, once they hatch out, excrete proteins. So much of life is proteins. Proteins are the most important biomolecule of life. And these proteins are extremely toxic to mammals, particularly to human beings. So the whole interest in this kind of simple, really, on a biological scale, very, very simple creature, it's been around for over 2 billion years on planet Earth, is the fact that it's very harmful to human life. So, why is that? Because these little teeny endospores have all of the elements of life needed to procreate. They have the plasmids, they have nucleodes, they have the plasma membranes, they have all of the necessary ingredients. Unfortunately, and this is one of the issues of interdisciplinary research, you have to figure out how to work across the lines. And when you work with materials like anthrax, you have to have a very high level of biological safety level, BSL, BSL-3. Very few people anywhere in the world have BSL-3 clearance, especially in the United States. So what we do instead is we look at surrogates. Bacillus genus is very common. There's many, many different organisms in this particular genus, one of which is Bacillus thuringiensis, shown here in microscopy. Very similar shape as anthrax, very similar endosporic behavior as anthrax. And these endospores are typically about a micron or a little higher in length and about a little less than maybe 0.8 micron in width. In other words, they're ellipsoidal in shape. And another good surrogate of the same genus is Bacillus cereus, which I'll show you in a minute. So we put the Bacillus thuringiensis into our terahertz spectrometer, and we saw one of the most dramatic signature effects that we had ever seen up to that time. This goes back about 5 years. We saw a very deep, about 20 dB deep signature right around 900 gigahertz. An overtone at around 1.1 terahertz, and then a ringing effect all the way up to about 1.4 terahertz. It's something we had never seen before in all of our experimental measurements of biological materials. So then we tried Bacillus cereus. This photograph shows the micro structure of a typical harvested sample. It's a mixture of cellular material, most of it dead material, just cellular walls and various other structures, mixed with endospores. You can see the teeny little endospores here kind of mixed in. And the transmission through this structure showed a very similar behavior as Bacillus thuringiensis that I just showed you. A very sharp peak and then a lot of ringing at higher frequencies. And so this sharp peak was distinguishable from the Bacillus thuringiensis sharp peak because it was lower in frequency. So a unique signature. So then we tried changing the hydration. Water is the solvent of life. The first thing you learn in biology or biochemistry is what a miraculous material water is. It's incredible material. In fact, there are philosophers or biophilosophers that say that without water, we would have no life on planet Earth. And one of the things that the astrobiologists look for in new planets is the presence of water. If they don't see water on that new planet, they suspect life may not exist or may have never existed. So we tried changing the water content, and we saw these dramatic, absolutely dramatic effects. So here is the signature that I just showed you in the last chart. And then we overhydrated it. We call it rehydration here, just because it's increasing the hydration to the same level as where we harvested the sample. And the signature disappears. And then we waited a couple hours and waited it to dry out. And the signature disappeared again. Here, it disappeared because of the fact that hydrated water has a huge background absorption in this frequency region. Here, it disappeared because the water provides polarity. Without water at all, there's no polarity. Without polarity, you have no absorption of electromagnetic radiation. So the bottom line is, in biology, and I think this is a generic statement, not just for what I'm talking about in the realm of spectroscopy, but in the realm of life itself, is hydration matters, and often matters a lot more than you first think. So next quick subject is we got into DNA and RNA. So what I've been talking about is bioparticles, toxic bioparticles, biological warfare, defense, topics that aren't very popular sometimes. Let's get into something more basic, which is nucleic acids. Nucleic acids are often considered as the informational content of life. They contain, every cell in your body has a unique nucleic acid structure that's unique to you as a human being. And that's true of every living organism on Earth. So we decided to look into that, and particularly DNA and RNA. And what we looked into was the building blocks of every DNA and RNA molecule, which are the nucleobases. And there's 5 basic nucleic bases: adenine, there's thymine, there's uracil, there's cytosine, and guanine. Cytosine and guanine forms all the backbone bonds in DNA and RNA. But in DNA, the adenine gets replaced by, in DNA, the adenine bonds to thymine, and in RNA, the adenine bonds to uracil. In other words, there's an exchange between thymine and uracil, depending on whether you're DNA or RNA. Nevertheless, these are probably the most fundamental molecules. And so we looked in the terahertz spectra of these. And every single one we looked at had a unique signature somewhere in the terahertz region. The lowest frequency one was thymine. The highest frequency one was guanine. And these signatures, what's remarkable about them is they're taken at room temperature, and they're taken without any special concentration effect. These are just guanine in its state that you would buy it out of a bottle from Sigma Aldrich, which is a very popular company for biochemical materials. The other thing is the absorption coefficients are huge. They're on the order of 20 to 30 inverse centimeters, which in the scale of things makes them very easily detectable in biosensors. So finally, I want to show where the state of the art is in this field. We have come to a point in time where almost any physical or chemical problem that you encounter can be simulated on a computer. And what I'm going to show you is simulations taken off our own cluster just in the last few weeks that show these signatures that I just represented in the frequency domain, and show them as seen using molecular dynamics. And if any of you have ever heard from molecular dynamics, it's one of the most powerful tools in chemistry and biology and now in biophysics of representing biological systems. Incredibly powerful. So, as an example, and hopefully this will get started, there it is. So what we're looking at here is a supercell in the thymine crystal that I just showed you. This is a crystal made up of thymine molecules. It's 240 unit cells, Each unit cell is 4 15-atom thymine molecules using that ring structure that I just showed, and 4 additional water molecules. And what's fascinating about this is that you see that the vibration is fully coherent. Across all of these unit cells, the vibration is coherent from cell to cell. And that's what makes it observable, and that's what makes it exciting from a biological standpoint, because it means that we can possibly treat these kind of molecules with external radiation. We may be able to excite them. We may be able to inhibit certain diseases. We may be able to even change their biochemistry on an instantaneous basis. Finally, nanofluidic chips. I promised to show this earlier on. Everything I've shown you to now was taken through paper, filter paper, that goes back centuries. Let's get high tech for just a minute. Here is a nanofluidic cell that is made by defining submicron channel photoresist using interferometric lithography. That's this step right here. Here's the photoresist. The scale here you can see is about 150 nanometers, 0.15 microns, pretty small. And then defining silica nanoparticles by coating on top of these, so basically embedding these submicron photoresist features inside a photoresist, and then calcinating. And calcinating is an interesting material science process, very high temperature, and it does 2 things. It blows off the photoresist, because photoresist is a polymer, and it just basically evaporates, and leaving behind a sintered layer of silicon dioxide. So it's a really interesting technology. It's been out there a couple of years, but it's a way of creating very long, and by long I mean millimeters long, nano channels. You can only see through the ends here, but these go on for millimeters. And what does that do? That creates the ability to see a new type of signature in submicron scale biomolecules. Everything I've shown you so far is micron scale. What happens when we deal with submicron scale? Well, guess what? RNA, DNA, proteins of all sorts are submicron biomolecules. So here's some incredible spectroscopy that we obtained on small interfering RNA, not necessarily physiologically relevant, but medically relevant, because siRNA gets used for a lot of diagnostic techniques in medicine, including flu diagnostics. And we've seen the most narrow signatures we have ever seen in the Territz region. These are so narrow that the Q, quality factor, if you're familiar with that term, is on the order of 100, which is unheard of in this frequency region. So this is a relatively new technology. It's high tech, it's nanoscale, it's submicron lithography, and it's already showing promise of detection of signatures in biomolecules with unprecedented sensitivity. Lastly, let's look at something that is naturally occurring. And if you do medical research or biomedical research, this question gets asked in every proposal you write, whether it's to the National Institute of Health or the National Science Foundation. Show to us that you are medically relevant. And what does that mean? That means, could your technology apply in a clinic, in a hospital, and help human medicine? So here's our first step in that direction. First step. Lambda DNA, 48,502 base pairs. It is perhaps the best understood of all naturally occurring DNAs. It's also very interesting from a human health standpoint, because it is the primary phage for E. coli. E. coli is one of the biggest contaminators of water around the world. Here's an article to prove that. We have seen our first signatures in this same region. And what's interesting about this is it's the same region. We seem to be seeing a lot of these in the same region. We don't know why. Why is nature being so consistent? 800 gigahertz to 1.1, we see one signature, two signatures, maybe a third signature, albeit the signal-to-noise ratio is not as good as those previous. But this is a much larger molecule. So just on a lark, we measured the sensitivity. Every biosensor, you have to know how sensitive you are relative to the molarity of the bioparticle or molecule you're detecting. So we did an experiment. We counted the concentration. It was 100 attomolar that was applicable to this chart. Now, some of you may or may not know atto. I'm sure you've all heard of giga, pico, nano, but do you all know what atto? Atto is 10 to the minus 18 in scientific units. That's small. So we were able to detect 10 to the minus 18 attomolar in this particular experiment, all made possible by that nanofluidic chip. So in summary, I hope I have motivated the fact that there are real biosignatures in bioparticles. I think our most obvious demonstration is these bacillus spores, like the anthrax surrogates. Those are so strong, they're really unmistakable. I think next in line is the nucleobases, the backbones of all DNA and RNA molecules. I think the technology is now getting to the point where we're changing the landscape. Nanofluidic chips are critical, and I've demonstrated that for you. The biggest biomolecule we've detected is lambda DNA at a concentration of around 100 attomoles. And I think a key message I want to leave with you is that water is very critical. Not only is it critical in biochemistry of all sorts, but it impacts our ability to detect these biomolecules and bioparticles. And ultimately, our goal is to treat or change the condition of these bioparticles and biomolecules using this kind of radiation. So thank you very much. And I wanted to you will quickly learn when you start doing research, you have to keep your investors happy. And you can quote me on that one. Thank you.
Thank you, Dr. Brown, for sharing your time and your research with us tonight. Next, I'd like to introduce Tournament Co-Director C.N. Chalker to lead us in the Science Olympiad pledges.
Welcome. The goal of Science Olympiad competitions, as embodied in the Science Olympiad Code of Ethics, is to give one's best effort while displaying honesty, integrity, and sportsmanship. All participants are expected to display courtesy and respect towards one another. Our collective example, as stated in the Science Olympiad pledges about to be recited by representative participants, will promote the spirit of cooperation among all participants. First, representing the student competitors are Weston McNish and Ashton Dahm from the Treasure Valley homeschool teams. Science Olympiad encourages participation from all types of schools, including public, private, charter, and homeschools. We are extremely proud that there are several homeschool teams representing their states this weekend, including both Division B and Division C teams from Idaho.
I pledge to put forth my best effort in preparation for the Science Olympiad Tournament and to uphold the principles of honest competition. In my events, I will compete with integrity, respect, and sportsmanship toward my fellow competitors. I will display courtesy toward event supervisors and tournament personnel. My actions will exemplify the proud spirit of my school, team, and state.
Thank you, Weston and Ashton. Next, representing the coaches are Mary Ellen Buckley and Nan Burkhart from Daniel Wright Junior High School in Illinois. Daniel Wright has been a regular presence at the national tournament for many, many years, in no small part due to the steady guidance of these ladies that they have provided. Both Mary Ellen and Nan will be retiring this year and have created an amazing legacy with numerous students they've coached over combined 30 years in Science Olympiad. Ready?
On behalf of the coaches and assistants at this tournament, I pledge to encourage honesty and respect for tournament personnel, our fellow coaches, and other team members. We want our efforts to bring honor to our community and school.
Thank you, Mary Ellen and Nan. And now representing the parents is Tricia Kearns from Fossil Ridge High School in Colorado. Each year at the awards ceremony, one team in each division is selected for the DuPont Team Enterprise Award for the best overall team performance outside of the top 10 placing teams. To be eligible, teams may not have attended last year's national tournament. Fossil Ridge was a Division C winner last year.
On behalf of the parents and spectators, I pledge to be an example for our children by respecting the rules of Science Olympiad, encouraging excellence in preparation and investigation, supporting independence in design and production of all competition devices, and respecting the decisions of event supervisors and judges. Our examples will promote the spirit of cooperation within and among all our participating teams.
Thank you, Tricia. And last but not least, representing the event supervisors is Dennis Papish. Dennis Papish has been involved in Science Olympiad for nearly 20 years, and for the past decade has been the national event supervisor for various wheeled vehicle events. He will be running Scrambler tomorrow, and if we are lucky, might even wear his Mickey Mouse hat like he always does, often.
On behalf of my fellow supervisors and tournament personnel, I pledge to run my event with fairness and respect for all participants and their coaches. Our actions will reflect the principles of Science Olympiad program and display the pride we feel as representatives of our colleges, universities, companies, states, or organizations.
Thank you, Dennis, and good luck to all of you tomorrow.
Well, this brings us to the end of our opening ceremony, and we have just a few housekeeping announcements to make. Students, your swap meet will be held in the McLean Gym. The McLean Gym is directly behind the stage. Please exit the arena on either side of the stage. Coaches and event supervisors can gather near the stage for your meetings. Keep in mind that T-shirts and official apparel will be available for purchase on the 4th floor concourse of the arena. I'd like to thank all of you for coming, and once again thank all of our sponsors who are making this event possible. Have fun and good luck tomorrow.